So we're going to work on identifying linear functions today, and we're going to work together on this foldable. And if yours is not already cut out, then you need to cut it out. But if you look, mine is ending, and yours would look something like this if it needed to be cut out, where the one that I am using has already been cut out. So if you need to, pause the video and trim your foldable. What we're going to do on the foldable, the way we are folding this, let me pan out a little bit here, is we are going to, if you look on this side, I'm going to fold this top down so that I can see the words identifying linear functions. So I'm going to fold that down, and at the top, it's not going to move it just however. So crease that there, like that. So you can see the identifying linear functions, and then it will lift up. And then you need to, and you don't have to do this now, you can do this later, but just cut on the top one so that you have like 3 little doors that will open up. So what we're going to do today, as you can see on this foldable, is we're going to look at different ways to identify linear functions, and the different ways that we're going to be identifying them is by looking at a table, looking at an equation, or looking at the graph. So first thing we're going to talk about is looking at a table. So we have already discussed what a function is. So we know that in order for it to be a function, all of the x's have to be different values. What we're adding on today, sorry about that, is that not only do all the x's have to be different, but we're also going to put some other conditions in it. So first thing, looking at how to identify a linear function using a table. So I have some examples here, but first, if we're trying to identify a linear function by looking at a table of a linear function will have a common difference. So a common difference between x's and the y's. So you'll have a common difference between the x's and the y's if it is a linear function. So this is what I'm talking about. So if we zoom in a little bit here, I'm going to show you some examples. So on this first one, we look from here to here, we add 1, and from here to here, we add 1. So there is a common difference among the x's right there. Over here, if we look in the y's, from here to here, we add 2, and from here to here, we add 2, and that is also a common difference. So the difference between the x's and the difference between the y's is the same. So this one would be a yes. So this is a linear function. All right, looking at this table, from here, let me change colors so you can tell the difference between each question. So between these two, we add 2, and between 5 and 7, we add 2. So that looks good. If we go over here, between 12 and 7, we subtract 5, and between 7 and 2, we subtract 5. So we have a common difference among the x's and among the y's. So this is a linear function. All right, looking at the next one. So this one down here, between 1 and 2, we add 1. Between 2 and 3, we add 1. So that looks good over here. On this side, from here to here, we add 1. From here to here, we're adding 3. So we have a common difference in the x's, but we don't have a common difference in the y's. So this one is not linear. So we have to have a common difference between the x values and the y values. All right, so looking at the last one. So from here to here, we subtract 1. And from there to there, we subtract 2. So that doesn't match, but let's see what happens on the y side. From here to here, we add 2. From here to here, we're adding 4. So what I'm noticing is that when I added 1 over here, or sorry, when I subtracted 1 over here, I added 2 over there. When I subtracted 2 over here, I added 4 over there. So what that tells me is that I skipped a step in here. And if I could go in and fill in that step, which we can do, this one would be a 4, and this one would be a 9, and that would continue the pattern of adding 1, and then subtracting 1, and then adding 2. So this one is, yes, it is a linear function. So again, in order to determine if a linear function, if a table is a linear function, you're looking for a common difference between the x's and the y's. All right, moving on to the next tab, we're going to look at how you can tell if a linear function or if a function is linear, sorry about that, by looking at an equation. So if we open this one up, so the equation of a linear function will not have. So what I want you to pay attention to on this is that these are the characteristics that will not be in an equation. All right, so first thing, that a linear equation will not have x squared or a y squared or an x to the third or an x to the fourth, ... So it's not going to have exponents on the variables. All right, the next thing that a linear function will not have, so that's our first one. The next thing that a linear function will not have is x and y multiplied together. X and y cannot be multiplied together if it's linear. All right, next thing that a linear function will not have is a square root of x or a square root of y. So your variables are not going to be inside square roots. All right, the next thing that a linear function will not have in its equation is x as the exponent. So 3 to the x, or it won't have 2 to the y. So you cannot have the variable as the exponent. All right, another thing that cannot happen on a linear function is you cannot have only an x in the equation. And we kind of talked about this the other day when we were doing the vertical line test, but when you have only an x in the equation, that's going to be the equation of a vertical line. And when we do the vertical line test, we know that that one is not possible. All right, and then the last thing that a linear function will not have is something like 7 over x, or I'll just say 2 over y. It cannot have that. Now, it could have an x over a y, or a y over an x, but the fraction can't have just one variable in it without the other. All right, so I have a couple of examples below. So if we look at this one, y equals 2x plus 5. So it doesn't have any exponents. The x and y are not multiplied together. We don't have a square root. The x and the y are not listed as exponents. We have a y in the equation, so there's not only an x, and we don't have anything in fraction form. So this one is linear. All right, next one, right here. So we look at this equation, y equals 3x squared minus 9. Well, we have an x squared. So that's our first one. We cannot have exponents on our variables, and we do. So this one is not linear. It can still be a function, it's just not a linear function. All right, the next one. Y equals 4 over x. We don't have exponents. X and y are not multiplied together. The square root of x or square root of y is not in the problem. The x and the y are not written as exponents. We don't have only an x, we have a y in there, but this last one is an issue. This one looks similar to that. So this would be not linear. All right, and then last example, by looking at an equation, we don't have an x squared or a y squared or any other exponent. X and y are not multiplied together. We don't have a square root. The x or the y is not an exponent. We don't have only a an x in the equation. We do have only a y, but that wasn't listed as a problem. What can't happen is only an x. And it's not written as a division problem, so that makes this one linear. So that covers how to determine whether your function is linear by looking at a table, which means that we have common difference. We've got some patterns going on there. And now we've been through how to tell with an equation, which is looking at those characteristics at the top make them not linear. All right, so the last tab we're going to look at is how to determine if our function is linear by looking at the graph. And this one's pretty easy. The graphs are very, very nice. I should mention that you can tell by the graph if a linear function is linear or if a function is linear because it makes a line. So the graph of a linear function makes a straight line. It's that easy. So what we're going to do is look at our graphs below, the examples that we have, and determine whether these graphs are linear or not. So we look at the first one. This makes a straight line. It passes the vertical line test, so it's definitely a function, and it makes a straight line, so this one is linear. All right, looking at this example right here, so it passes the vertical line test, so it's definitely a function. The problem is that this isn't a straight line. It's actually, if you could look at it, you could say it's an angle, if you want to think of it that way. It's a ray going in that direction and a ray going in that direction. I would not call this a straight line, so this is not linear. So linear has to be a straight line on the graph. Go down here. I don't think we need to discuss this much. That one is definitely not a line, so not linear. And then we look at this one. It is a function, and it makes a straight line. So that tells me that this graph is linear. All right, so next up, we want to glue this into your spiral, and then we're going to do a few more examples to make sure that you understand the concept of identifying linear functions.